Thank you very much for inviting me here and making me the speaker here. I leave tomorrow, so it's the last possibility for me to give a talk. The results I'm going to present here were published in several papers jointly with Mikhail Solomiak from Rehovot Weizmann Institute. A couple of years ago, I was one of the organizers in the program at Metallifler Institute in Sweden, devoted to Hamiltonians and magnetic fields, with magnetic fields. But it turned out that quite a lot of big part of participators were willing to give a talk about something without magnetic fields. So in order to somehow accommodate them, there was a formula which was invented that in the beginning each such speaker said that we suppose that the magnetic field equals 0. I'm in a similar situation here because the program is devoted mostly to periodical problems and something of the sort. There will be something periodical in my talk, but mostly it will not be periodical, but something more general. And in this case, it's supposed that the period equals 0.
Infinity, rather, yes.
0. Periodic function. Well, so we are going to discuss eigenvalue estimates for Schrödinger operators on infinite combinatorial metric graphs and what is the problem. So on the abstract level, what is the abstract Schrödinger operator? We have some non-negative operator H0 in a functional Hilbert space. It's important that it's Hilbert space of functions. L2 of x, where x is space with measure. V is a real function. And we consider the Schrödinger operator. It is H0, which, so to say, the kinetic energy operator, and V is the potential energy operator, and alpha is the coupling constant. The question is about the number of negative eigenvalues of this operator. The notation is n minus of H alpha, or simply n minus of alpha, or the number of these negative eigenvalues when it is finite, and the most important thing is the dependence on the coupling constant. Alpha grows to infinity. This, in fact, is a very old problem, probably more than 100 years old, for different classes of operators, and it is related. So the results, the eigenvalue estimates, have been used in quite a lot of various applications, including the ones in scattering theory, in stability of matter, in approximation theory, and so on. One of the most close to me topics here is the asymptotics of eigenvalues, which in many cases can be obtained on the basis of estimates of eigenvalues. So, of course, the leading classical example is when the Hilbert space is the usual L2 on the d-dimensional Euclidean space. The operator is the minus Laplacian, and here I should start with the quasi-classics result, the estimate whose name I carry. So it was proved by myself as long ago, it's 72, and then by Lieb in 76, one more method in 77, and it is called the CLR estimate. And there were 3 different proofs at a different time, and then some more people joined. So the most recent proof was published only something like 2 years ago only. And in fact, this problem was considered to be important. At least 2 of the proofs were invented by Fields Medal holders, by Shinton Yao and Charles Pfefferman. So what is the estimate? Here we'll tell something which is not always in the textbooks. So suppose the dimension of the space is bigger than 3, is 3 or greater, the potential belongs, V is potential, belongs to L d half, then there is some constant CD depending only on the dimension but on nothing else, so that the number of negative eigenvalues is estimated from above by the integral of V to the power CD times this coupling constant to this power. Moreover, so this estimate is sharp in the sense that there is also, under the same conditions, there is the asymptotics with some, again, constant depending only on the dimension, then as the coupling constant alpha goes to infinity. So it's usual to say a constant goes to infinity, but sometimes Planck constant goes to 0. So it can happen that constant moves somewhere. So there is the asymptotics, this one. What is remarkable here, that there is also an inverse result. So if the estimate of the sort 0, 1 holds, then necessarily V belongs to this class. And of course, automatically the asymptotic is valid. So there is a kind of cut-off. So the number of negative eigenvalues cannot grow as alpha grows slower than alpha to this power, to the d half.
And CD is known or not?
What?
CD, the constant.
The constant, well, it's a lot of unfinished work, so it is not known. The best constant it is not known. There is some gap. You see, this constant CD cannot be smaller than the asymptotic coefficient here. And depending on the dimension, there is a gap. For example, in dimension 3, I think gap is something like 2.5 in the ratio.
So for inverse, you mean if 0, 1 holds with some constant instead of the integral?
Yes, if there is the estimate with this dependence on this dependence on the coupling constant and with some number instead of the integral, then the integral must be finite. Well, so it was very, very long ago. Considerably later, so there were some other important things to do. Considerably later, yes, one more thing to notice here. Another feature is that the asymptotic behavior and estimates for this number of negative eigenvalues does not asymptotically depend on the geometry of potential. Doesn't depend where in the Euclidean space does it live. So, what can be said about more general case? So, which structures in the Euclidean space, which particular properties of the Laplace operator are responsible for this kind of estimates? Considerably later, so it was in late 90s, together with Slamiak, we found out that, in fact, this result is much more general than the one for the Euclidean space. So the Euclidean space, D, can be replaced by any space with measure. The operator, Laplacian, may be any self-adjoint operator, instead of Laplace, any self-adjoint non-negative operator. The only thing that it must generate a positivity-preserving semigroup. So the semigroup, the heat semigroup, generated by this operator, P of t, must be positivity preserving. So this means that if we apply it to a function u, then the absolute value is not bigger than the semigroup applied to the absolute value of this function. It's called positivity preserving. In other words, it maps positive functions, non-negative functions into non-negative functions almost everywhere. And for the heat kernel, for this P, it is the integral, this P of t, it is the integral operator, it can be proved. For the heat kernel P of t xy, so it's the kernel of this heat semigroup, one should have the estimate, so if we denote by P of t small, the norm of this operator, P of t, as acting from L1 to L infinity, and it is the same as this essential supremum for given t. It should satisfy estimate, one estimate near 0, this one, and the other one at infinity, this one. So it may be of different order. And these exponents, delta and d capital, are called local dimension and global dimension of the operator. Under these conditions, as they're shown here, one can get the generalization of the CLR estimate, which was discussed before, so that the number of negative eigenvalues of the Schrödinger-like operator can be estimated by such a strange expression, which can be for particular cases of P calculated or estimated. So you can write in this form, and you see the coupling constant alpha enters in some strange way. However, so here again, we will discuss these estimates a little bit more, and I here read the contents of the exponent delta and d. So you see the function p, so this means that the estimates for the heat kernel, it should have estimates of growth as t goes to 0, and another estimate as t goes to infinity, this one. So the particular case where everything started, when we have the Laplace operator, in this case it is well known. So the expression for the heat kernel is very well known. So in this case, delta and d are the same. They equal the space of dimension. And this estimate, the estimate for the heat kernel, also well known. And this immediately gives the estimates CLR, so the estimate in the Euclidean space.
Sorry, Grisha, what did Zwicky do? He also did something with positivity preserving.
No, he didn't use this.
No.
So a remark that in a very recent paper, Rupert Frank, using a new approach to spectral estimates developed by Raymond, removed the requirement that in the case delta equals d, this one, the requirement of positivity preserving property. So even this is not quite essential. Well, geometrically, what do these exponent delta and d mean geometrically? So delta is the dimension of X, the space where everything happens, as seen from a very close distance. So I just can draw a picture. So you have some X. You come very, very close to it and see some very, very small parts. The dimension when you see from very close distance is this delta. D, large D, is something of X as you see it when you go very far. Look at it from a very large distance. You cannot see the details and even take off your eyeglasses. And this is the dimension what you see. I give an example that, for example, if we have in the desk the lattice. What is its local dimension? I come very close, see 1 point, dimension is 0. What is the global dimension? I go very far away and look there, and from large distance the points are almost the same. I see the plane, so the global dimension is 2. Well, suppose we have here some say 3-dimensional, so you can imagine so that this line represents some thick 3-dimensional pieces connecting the points. And again, it fills all the desk. When you come close, you see something very thick. The local dimension is 3. When you go far away, you cannot feel that these intervals are fat, and you think that the global dimension, as it seems seen from far away, is 2. So this is the geometrical, the very rough geometrical meaning of this constant delta and d. Well, the interesting case is when this delta and d are different. It's possible that the local dimension is smaller than the global one, or the other way around. And in this talk, we are interested in the case 1, small local dimension. In this case, one can, the formula which is given, the general formula can be written in a more simple way. In a more simple way. So it consists of 2 terms. The integral of v over the set where v is large to the power, to this power, and the integral of v of over the region where v is small to another power, to a larger power. And it is seen from this that if one replaces here the local dimension by the global one, delta by d, the sum becomes larger. So as a roughening of the result, one can write also the estimate for the eigenvalues in the case of small local dimension in the same way as for the Euclidean space, for example. The main observation here, so it's a roughening and it's not that interesting, and the reason for this estimate being non-interesting that such estimates are never sharp. Do you remember that in the Euclidean space when delta equals d, the estimate was sharp? Here it's never sharp, because if the right-hand side here is finite, then in fact not only the estimate holds, but it's in the order of alpha, it's so small. So the estimate is not sharp in the, or I forgot the factor, so the factor alpha to the power d half here is missing, sorry. So the cutoff property doesn't exist. So instead it is possible by the choice of v to get these n minus the number of eigenvalues to have any prescribed order between local and global dimension. So the question is to find some better results about some more concrete situation here, and typical examples which we are going to consider here are combinatorial and quantum or metric graphs. The reason is that more detailed information can be found than in the general case. So something periodic now. So we consider the Schroedinger operator on the cubic lattice, ZD. What can be said about this case? So X, the space with measure, is the lattice with the counting measure, and we consider as the operator is the Laplacian, the discrete Laplacian, it's given here. And what is the spectrum of this operator? It can be found explicitly very easily. So it's the interval from 0 to 2D, it's absolutely continuous, and so on. And even the heat kernel can be found explicitly by means of Fourier series. This is the formula which can be used in different cases, but it helps. In this case, when we have the lattice, I have already explained to you that the local dimension is 0 and the global dimension equals d, the dimension of the lattice. This explains some peculiarities in the behavior of the spectrum. So what does the general theorem then say? It says that the number of eigenvalues with coupling constant included is not greater than some universal constant times this power, and one should take the sum of this v. And this holds as long as v belongs to, you see, it's L small because it's a sequence. This v is a sequence. It's called the discrete CLR estimate, and it has the same shortcomings as in the previous case, as in the general case. So similar. So it is similar to the CLR estimate, but it's never order sharp. So this means that here we have this constant, this power of the coupling constant. But in fact, for any v here, the order is, the decay rate is smaller.
But is it a special case of the previous theorem?
Well,
Does it not fit in the abstract?
yes, it is. It is a special case, but here we can say much more.
Okay.
So here, for example, we can have. Here we can, in this particular case, we can find also sharp estimates. So we say that we introduce the weak norm, the weak LQ norm. So it's similar to Marcinkiewicz spaces. So if V belongs to a little bit larger space here, then still we have this estimate. But this estimate is order sharp, so it can be complemented by similar lower estimate by this quantity. So this means that LQ, this one, is a wrong space to study. So this all is obtained using the particular and very explicit information about the heat kernel for the discrete Laplacian on the lattice. Now the question is, and here I lose periodicity, to extend this kind of results to considerably more general graphs. But the graphs should be infinite so that the unperturbed operator has continuous spectrum. So we introduced the notion of weighted combinatorial graph. So what is a combinatorial graph generally? It is a set of vertices. We suppose that it's infinitely many vertices. It's denoted by V. It is the set of edges. So some vertices are said to be connected with edge. And the notation tilde means that two vertices are connected by some edge. It's an important notion that the degree of a vertex, it is the number of vertices by which it is connected, and we suppose that it's finite for any vertex. We always suppose, it's not that important, but it's convenient, that the graph is connected, has infinitely many vertices, and has no loops, no vertices with degree 1 or multiple edges. It can be written, what does it mean? So this is a loop, so the starting and ending point of some edge is the same. This is the case of degree 1, so we can get here no other vertices. And multiple edges, it is that there are several edges which connect the same pair of graphs. So all these three cases we drop. So with each edge, so why is it weighted graph? With each edge, we associate a weight, GE, some positive number. We introduce a counting measure on this graph, so the measure of any vertex equals 1, and the main helper space is M2. So what is the operator? What acts as the generalization of the Laplacian? So the easiest way to define an operator is to define it by means of the sesquilinear form, by the quadratic form. So it is the following sum. So the quadratic form of the operator acting on the function. The function is the collection of values at vertices. So it is this sum defined on L2 function where it is finite. And this sesquilinear form, this quadratic form, defines a self-adjoint operator which we call the Laplacian on this weighted graph, weighted Laplacian. How does this act? One can write explicitly how does this operator act. So you see, it acts in the following way. So the value of the operator acting on function in point V equals this sum. One should take such difference.
Divergent operator.
Yeah. And here one has this. These weights. I remind you that for the case on ZD, we has the same sum, but there was the coefficient 1 here instead of the weight. It will be clear a little bit later why are these weighted crucial. So we set the length of the H equal this, which equals this weight, the inverse value to this weight, and so we assign a structure of metric space to the graph G. And we, having an operator, having space, we can define semigroup, and supposing that weights are bounded, form a bounded set. Geometrically, this means that there are no points which live no edges of infinite, of very large, of unboundedly large weight. So we can consider the operators, they are semigroup, and of course they are bounded since everything is bounded, and the local dimension is 0, as I have already explained to you several times. When we get very close, the local dimension is 0. But the global dimension, so our main assumption here about the global dimension is the rate of decay of this semigroup as t goes to infinity. For some d, it's supposed that it's larger than 2. You see, they are specialists in graphs, and more generally in heat semigroups, such people as Coulomb, Grigorian, Salovkost. They worked quite a lot in such estimates and had found many equivalent conditions for geometric conditions for this P of t to decay in this way. In particular, it is given in the terms of Sobolev time inequalities or isoperimetric inequalities. So it's more or less well understood stuff. So it's more or less even for general.
Can you understand them in terms of growth of walls of?
It's exactly the isoperimetric
Okay.
kind of estimates. So theorem for weighted graphs, it says that suppose that V, the potential belongs to LD half on this graph, then one has this kind of estimates. So on the one hand estimates, on the other hand one has the O small term, so the estimates is not sharp, and this holds for Q belonging to the interval between 0 and d half. So this is for nice potential.
This estimate is true for which alphas sufficient.
Yes, of course. It depends on which, no, alpha. It's as alpha goes to infinity. It depends on which d, which q.
The first inequality is only for large alpha or
Конечно, находится V. Then it will be clear.
This is the estimate. The estimate. And in applications, it is important to have this inequality for all alpha.
But you could have written it without alpha. You could
Yes,
have
of
said
course,
it
of
would be
course,
clearer.
of course. One can put alpha inside V, and
Then it will be clear.
yes. So it's important that
Equation will disappear.
yeah, that the constant doesn't depend on V, and it holds for all alpha, or for all V. Well, so this is, now we pass to a little bit more intricate object, is metric or quantum graphs. What does it mean? Again, we have a set of vertices, a set of edges, but each edge is not simply some abstract relation saying that this one and this point is this vertex is connected to another one, but it is considered as a line segment, which with all structures of a line segment. So with this gamma, we associate a combinatorial graph with the same set of vertices, the same set of edges, the same connection relations, and we assign to each edge of the quantum graph, we assign the weight, exactly the formula which is given. So there is the rule which associates with the metric graph a weighted combinatorial graph. And it turns out that the spectral properties of these two objects are closely related. It will be seen soon. So some notations: the star of the vertex, it is the union of all vertices which are connected with this one. The star of the edge, so it's the union of the stars of the endpoints. And the Lebesgue measure, so on each edge is a line segment, there is a Lebesgue measure, and therefore we have a measure on the whole quantum graph, and L2 with respect to this measure is the main Hilbert space where everything happens. So one can understand the element in L2 of gamma as simply a collection of functions on edges, not related. Now the Laplacian. On each edge, the Laplacian acts as minus second derivative. Note the font here, because you see this space, the Laplacian here it is denoted, the Laplacian on the quantum graph is denoted by this Cal font, and on the corresponding Laplacian on the combinatorial graph is used by usual font. So the matching conditions. So the operator, it requires also the matching conditions at the edges. So the operator should, the functions where it is defined should be twice differentiable on each edge inside. And the matching conditions that the functions in the domain of operator must be continuous at each vertex and satisfy the Kirchhoff condition. This is given. It's the most natural one, but not necessarily. One can write something more general. So the leading example here, so it's called the Exner-Last graph. We take the graph is the following. We take the points in the lattice and connect them. Connect the neighboring points by intervals with length 1. And this is called the Exner-Last graph. It's easy to calculate the spectrum, which is a little bit peculiar. So the spectrum of the Laplace operator on this extra last graph consists of absolutely continuous component which fills the positive semi-axis. And also there are infinitely degenerate eigenvalues at the points pi square times k square. They,
Relations of edges, yes.
yeah, so it's exactly the ones going along edges and somehow matching, so that there are only finitely many of them. So this is the spectrum, and but generally, well, here again we have something periodic. Well, what the relations between the Laplace operators on these two graphs? So you remember that having a general quantum graph and a Laplace operator there, this is the one, we associate the weighted combinatorial graph and Laplace operator there, and what is the relation between them? The fact which we proved is the following. Suppose that the lengths of edges are bounded from above and from below. Then the global dimension of the metric graph equals the global dimension of the associated combinatorial graph. Do you remember that it can be very well understood from this geometrical, very rough geometrical point of view, that if we have these points, then when we go far away, very far away, we cannot feel the difference. Are these points connected with each other or not? But there's a general fact that the global dimension is the same. And if the degrees of vertices are bounded from above and the lengths are bounded from below, then we cannot be sure that the local dimension is 1, because there may be some pathologies, but the local dimension can be taken as the local dimension of the quantum graph can be taken as close to 1 as we wish. But we cannot be sure that it can be 1. So the Schrödinger operator, so we take a potential V being an L1 local functions on gamma. So what does it mean? It is that we have some V, some potential V on each vertex, on each edge. So it's a collection of functions on edges. So we study as before the number of negative eigenvalues of the perturbed operator, and it was found out that the spectral behavior of the Schrödinger operator is governed by two completely different objects. One of them is the spectral behavior of the discrete operator, the operator of the discrete graph, where with some efficient potential Vd, which is obtained from V by taking some weighted integral for each V, for each vertex. This is a weighted sum of integrals over the edges which contain this vertex. And the other object which governs the spectrum is the spectrum of the union of operators of Dirichlet problems for such simple operators. So it's the Schrödinger operator on each edge with Dirichlet boundary conditions. So simply one should, for any edge, depending on of its length and of the potential, calculate the spectrum, this sequence of eigenvalues, and then take the union of all these spectra. So there are two objects. One of them is responsible for the discrete structure of the graph, and the other one is responsible for what's happening on edges. So the question, which of these two objects, so we have two different spectral properties, which of these two objects produce more eigenvalues, gives a larger contribution to the eigenvalues of the Schrödinger operator. One might expect that the second one, because you see here we have one-dimensional problem, a zero-dimensional problem. Here we have one-dimensional problem, and one-dimensional problem has essentially more eigenvalues, more flash to give eigenvalues, but the result is wrong. So under the so this is the general fact that which just make more concrete the words I said, that the eigenvalues of the Schrödinger operator on the quantum graphs is determined by the eigenvalues of the discrete, of the combinatorial graph, and the eigenvalues of Dirichlet. But in many cases, for example, when V belongs to LQ and gamma, and in some other cases, when Q is, the second term is absorbed by the first one. So it turns out that if the potential goes to zero at infinity, so to say, sufficiently fast, so it belongs to this LQ, which is smaller than d half, and in many other cases, the main contribution to the eigenvalues behavior of the Schrödinger operator on the graph is determined by the corresponding structure on the combinatorial graph, and the edges which the spectrum of these operators on edges, they give a smaller contribution. So this is again I written a paradox that although the one-dimensional part of the graph has more fat than the zero-dimensional one, the latter gives a strong contribution to the eigenvalues counting function. The estimate is sharp in the sense that one cannot put in these cases alpha or small instead of smaller. And again, in these cases, this means for fast decaying V, the geometry of the potential doesn't play part.
Sorry, can I just ask, I didn't understand. What was gamma and gamma prime?
These are some constants here.
They are
The-
fixed, right? Or
One can choose them as one wishes,
okay.
so that the sum of inverses equals 1, and one can choose them to get better.
So to get to the second line in the special case, you choose one gamma infinity, and the other you choose
Yes,
one.
exactly.
Okay. So the
Well, now an interesting thing here, what happens if the potential V goes to 0 more slowly than the general CLR estimate and all these calculations admit. In this sense, in the case of the Euclidean space, where we have the Schrödinger operator in the Euclidean space with potential V, there is a very fine boundary. So if the potential V belongs to LD half, then the spectrum is discrete and satisfies the asymptotic condition. But if it decays as
Negative spectrum.
so if V belongs to LD half, then the asymptotics of spectrum, as we discussed it, has the order alpha to the power minus d half, alpha to the power d half. But if V is has this order, then the operator may have a continuous spectrum, continuous negative spectrum, and you can see that the gap between this one and this one is very, very small. So it's very fine, fine boundary here, and of course one cannot admit that V decays even more slowly. So what happens in the graph case? So the potentials that decay slowly here in the graph case fit into the general theorem, and it gives we call it super-Weyl order. So we can there can be any order, depending on the potential. We see here that for they can grow faster than the degree of alpha. The existing results are very far from being complete. There are many reasons for that, even for the Euclidean space or for the lattice. But the general wisdom that opposite to the Weyl order estimate, the geometry of V is important. And we invented a construction, we call it construction with sparse potentials. So suppose we have a graph, and the potential consists of small islands which live very far away from each other, and zero between islands. Here we write it, so I do not want to, I have no time to go in details of the construction, but the result, the main result is the following. Suppose that this V consists of islands which are sufficiently far away. It can be made concrete. Then, first of all, the theorem says that any weighted graph contains an infinite sparse subset, so that these islands, the potentials there, are in a certain sense almost orthogonal. And we call the potential moderate if its values, the limit of this values Vn divided by Vn plus 1 equals 1, so it's not exponential. In this case, we prove that for any moderate sparse potential, there is the asymptotics. V is a moderate sparse potential, so it does the values in different points do not change very fast, and moreover, the points are sufficiently far away. Then the number of negative eigenvalues for growing alpha may have any prescribed order as alpha goes to infinity. So whatever order we like, we can make it. So this is a very strong difference compared with fast decaying potential, which do not feel where the potential lives, and it do not, and this situation doesn't feel how fast it goes to infinity. So similar results. So the results about sparse potentials hold for metric graphs as well. And I finish by saying a few words about the two-dimensional case. You see, in the very beginning of this program, there was an important talk by Zhenya Shargorodsky, who described his recent results about the eigenvalue estimates in the same problem which we are discussing now for the Schrödinger operator in the two-dimensional Euclidean space. It was found out quite long ago that the two-dimensional case for Schrödinger operator has quite a lot of difficulties compared with other dimensions. These difficulties are explained by different ways. For example, this is the only case where the green function for the Laplace operator changes sign. In the dimension 1 and in dimension high, the one with the green function is of constant sign. In dimension 2, it changes, it's logarithmic, it changes sign. The other thing that the green function grows logarithmically at infinity. And also it has logarithmical singularity at 0. All of this leads to quite a lot of complications, many pathologies in the two-dimensional case, not only as it concerns the spectral properties, but other cases other things as well. And therefore, the situation with eigenvalue estimates for the Schrödinger operator is still not in the still not understood, doesn't got its final solution, even in the case of the Euclidean space. The results by Shergorodski seem to be close to final, but they still do not give necessary and sufficient conditions. In the discrete case, in Z2, the situation is a little bit better. So we had to modify our approach and make it a little bit harder. So in particular, among pathologies which one has in the two-dimensional case, that there cannot be an estimate of the form with v to the power 1, d by 2 equals 1 in the Euclidean space. So there is no such estimate. So it is the logarithmic singularity of the green function which prevents it. So what did we get for the two-dimensional case on the two-dimensional lattice? So this is the final result I present, that for the Schrödinger operator on the combinatorial graph, on the two-dimensional lattice, one can have the estimate of this kind. So you see one has the potential V as it, but with such logarithmical weight. And the estimate is sharp that if this quantity is infinite, so if V decays at infinity a little bit slower, so that the sum is infinite, it is possible that there are infinitely many eigenvalues. So the result cannot be improved. So as a whole, it's partially it is an experimental science. So we may consider different special cases, and the special cases related with lattice seem to be the most interesting ones. And the methods which we apply, where different dimensions cooperate, these, in particular in the two-dimensional case, we have cooperations between two-dimensional Laplace operator, the Laplace operator on the quantum graph, and in the combinatorial graph with these three ones we're working, they can give rather advanced results about the eigenvalue estimates. So those who are interested can browse the archive papers by Solomiak and myself from 08 to 12, and it's easy to find as soon as one knows correct spelling of my name, and they are published in different journals, but it's much easier to find it on the archive. Thank you for your attention.
Thank you very much. Questions? I have one question. If we talk about classical Rozenblum deep Zwicky, what is your favorite proof?
Well, I think now the proof by Rupert Frank. But you see, actually there are interesting cases in eigenvalue estimates where my original proof on 1972 is the only one which covers the problem. You see, all existing 7 or 8 proofs both have some limitations. They use some conditions, and they do not overlap each other. For example, if one considers, I do not say it has any physical meaning. For example, if one considers the operator so this TU, and one is interested in the distribution of eigenvalues of this operator. So then one can get the eigenvalue estimates and even the asymptotics of the spectrum of this operator. However, it is only my initial method of 72 can provide it.
Okay.
But I'm afraid that this initial method is the most complicated one.
So Franz is the simplest or the most general?
Well, the important fact is that it works both for second order and for higher order operators as long as one has the estimates for the heat semigroup. And also it enables one to consider, for example, operators acting in functions with values in a Hilbert space and so on.
Okay, other questions? Okay, let us think.